Good evening. It's 7:30 in Dhaka, so we will get started. This is SK Ghosh. I would like to welcome all of you to the continuation of our training and capacity building program under Project S9 of Rajuk's Urban Resilience Project. We started this series of seminars in mid-March. Today is a continuation. Uh, Today is the second part of the Soils and Foundations provisions of BNBC 2020. Uh, Professor Zainul Abidin did the first part yesterday. Today's speaker, Dr. Ansari, was saying that Dr. Abidin didn't leave anything for Dr. Ansari to cover. That is not true, although yesterday's lecture was quite comprehensive. Uh, Professor Ansari will cover the geotechnical part of earthquake engineering. That's probably the shortest and the best way to put it. We are very lucky to have Professor Ansari as our speaker today. He definitely doesn't require an introduction to you. Many of you, I'm sure, are his former students, maybe his students now. He is a long-time BUET professor, and in addition, has played a major role in regulating garment factory construction, maintenance, etc., after the disasters that you are familiar with. So, without anything further, I would like to introduce Dr. Ansari to you, ladies and gentlemen.
Thank you, Dr. Ghosh, for the kind introduction. Let's start. Basically, what Professor Zainul Abidin has provided you, I think he has given you all the basic materials of geotechnical and soil mechanics. Because yesterday I was there on and off, and I have seen that he has delivered, because he has also taught us in undergraduate and master's level. So his lecture was very comprehensive. Okay. Okay. So the part I'm going to deliver is basically it will cover some part of chapter 2 and some part of chapter 3. Because as Dr. Ghosh has mentioned, that I will try to cover the soil related part, which is related with earthquake engineering. That means related with seismic or dynamics, you can call that. It is sometimes it is called earthquake geotechnical engineering. And in fact, Dr. Ghosh has delivered his lectures, and many of his lectures, I think he has covered many of it, but I will go a little detail probably, because in the code, in the BNBC, it is not given so much in detail related to the geotechnical earthquake engineering part, especially how to develop, because last time when I was listening to Dr. Rakib presentation, somebody asked how to generate the time history data for modeling. So I will also touch upon it, and also some part like one-dimensional seismic response analysis, which is very much essential, because in the code we have only provided the PJ value at the base of the, or we can say it on the rock, but how to convert it to the surface, because you need the PJ value at the surface to make the liquefaction analysis or some other analysis. So how to convert that, I will also touch upon that part. So, okay, if I start, say, I will start with 2.5 earthquake loads here. In 2.5.2.2, it is clearly mentioned that in the code, the characteristics of earthquake resistant buildings. Over there in the foundation bullet point, it is mentioned that the design and construction of the foundation and of its connection to the superstructure shall ensure that the whole building is subject to a uniform seismic excitation. That means it is mentioning that you need some continuity. If your structure is not connected properly with the foundation, the superstructure is not properly connected with the foundation, then during earthquake it will cause problem. And in many of the case studies, it has been seen that that kind of thing has happened. So you need proper connection with the foundation, both pile and shell foundation with superstructure. So the detailing is also mentioned in chapter 3. So over there it has been mentioned that for buildings with individual foundation elements like footings or piles, the use of a foundation slab or tie beams between these elements in both main direction is recommended. This is recommended also. Sometimes you need to bring out the rebars of the pile and connect it properly with the foundation slab like the pile cap, and also connect it properly with the column and other elements of the superstructure, so that when the earthquake load comes, the structure behaves as a monolithic structure. Okay, regarding the earthquake loads, it is Article 2.5.3.1. It is in the site investigation article. It is clearly mentioned that appropriate site investigation should be carried out to identify the ground condition influencing the seismic action. Generally, for for site investigation in Bangladesh, we generally practice or we generally perform only SPT, standard penetration test. For when you consider any seismic activity or anything related to dynamics, you have to also carry out additional investigation, like we need to perform PS logging, or sometimes it is called downhole method. Sometimes you have to also perform CPT, cone penetration test, as well as the SPT. And also sometimes you need to perform SCPT. It is called seismic CPT. So all these along with SPT, that means SPT, CPT, seismic CPT, and PS logging oblique downhole, these are required to establish the site parameters to make the modeling for the soil part. Generally, for buildings we model, but for soil you need to also model. You can perform one-dimensional modeling, you can perform 2D or 3D modeling, depending how much data you have. Generally, for one-dimensional modeling, it is very common to use the program called Shake. And for 3D model, generally we can use Plexis 3D. There are other software also, but this is very common, like for Shake for one-dimensional and 3D for Plexis 3D for 3-dimensional modeling to model the soil behavior. But the input required is generally obtained from SPT value, CPT value, seismic CPT value, and downhole oblique PS logging parameters. So appropriate site investigation should be carried out to identify the ground condition influencing the seismic action. It is clearly mentioned. So it is not clearly uttered here, but with site investigation, the methodologies or the techniques I have just mentioned has to be used. The ground condition at the building site should formally be free from risk of ground rupture, slope instability, permanent settlements caused by liquefaction or densification during an earthquake. So this part is more related with earthquake loadings. That's why it is clearly mentioned that ground rupture, slope instability, and permanent settlements caused by liquefaction or densification during an earthquake, the structure has to be free from this. So that means for this site where you are going to construct and for which you want to perform the seismic analysis, you need to study these issues. Third point, the possibility of such phenomena should be investigated in accordance with standard procedure described in chapter 3 of this part. So as Professor John Levinson sir has clearly mentioned, although probably he didn't have much time to describe, but he clearly, I have seen his presentation over there, he has clearly mentioned that SPT, CPT, and other techniques like other probably seismic exploration techniques he just mentioned in passing. So as I mentioned, along with CPT, seismic CPT, PS logging, and downhole method, you can also perform sometimes electrical resistivity. And also sometimes you may have to perform some other non-destructive testing like GPR, ground penetrating radar. because generally if you perform SPT, CPT, downhole method, these are all point method. That means probably after each 50 meter or after each 100 meter you can perform those. But in between, if you want to make a profile of the whole area, then you need to perform either GPR or electrical resistivity to get the detailing in between the two boreholes, either CPT or SPT or SCPT. And the last point, the intent of the site investigation is to classify, that is another issue. The intent of the site investigation is to classify the site into one of types like SA, SB, SC, SD, SC, S1, S2 as defined in section 2.5.3.2. I think this has been described in much more detail by Dr. Ghosh in his presentation, but we will use this and how to assess this one from the field data that we'll try to explain to you with some case study or some examples. Okay, in the earthquake load also 2.5.3.1 site investigation, it is clearly mentioned that for sites representing special soil type like S1 or S2, site-specific special studies for the ground motion should be done. So it is clearly mentioned in the code that site-specific study, that I will clearly explain later in my later slides, that you need to perform special studies, site-specific studies. Sometimes we call site-specific earthquake studies or site-specific seismic study that need to be performed because the S1 and S2 type soil is very poor, and for that in the code it has been recommended. And for soil type S1 have very low shear velocity, it is, in the code it has given some sensitive value. I think it is mentioned that it has to be less than 100. And low material damping can produce anomalous seismic site amplification and soil structure interaction effect. So if the soil due to the poor condition causes site amplification, then if a PJ value is recommended, say for Dhaka it is 0.15 G for a rock, but due to site amplification it may go as high as 10 times or 15 times. It has happened in Mexico City, but Dhaka soil is not that poor, but sometimes in Dhaka soil it may go as high as 5 times. And for S2 soil, possibility of soil failure should be studied. In site investigation part, again, for a structure belonging to seismic design category C or D, which is related more with structure, clearly it has been mentioned in 2.5.5.2 what is seismic design category C and D. Site investigation should also include determination of soil parameters for the assessment of the following. That means for C and D category, later we'll see that for Bangladesh, if you go to the seismic design category, in most of the, I think almost 70% or 80% of our country will fall in C and D category, according to the 2.5.5.2 article. So for those, you need to perform the following. You need to perform the slope instability, that is, then you have to perform the potential of liquefaction, that when liquefaction assessment has to be carried out, differential settlement has to be assessed, surface displacement due to faulting or lateral spreading if the faulting is present there, and lateral pressures on basement walls and retaining walls due to earthquake ground motion. So lateral pressure, when you design the basement walls, you have to consider the lateral pressure and you have to also consider the earthquake ground motion to assess that one. So if you go to that seismic design category of building, you will find that SD and AC, so the last two lines for all the SD and AC type, for all those occupancy category, the C and D type are recommended. That means the steps which has been mentioned over there, that means site investigation should also include determination of soil parameters for the assessment of the following, like slope instability, liquefaction assessment, differential settlement, surface displacement, and lateral pressure on basement walls has to be ascertained or has to be determined. Earthquake loads, then again, we are coming to the point where it is clearly mentioned that liquefaction potential and possible consequences should be evaluated for design earthquake ground motion consistent with pre-ground accelerations. So it is clearly mentioned. But as I mentioned, that in the building code, what will be the surface PJ has not been mentioned. So they have just mentioned what will be the 2,475 years ground motion, return period ground motion in the rock. But sometimes you also need to get the value of return period PJ value of rock of 475 years. Sometimes you also need to estimate the PJ value of rock at 200 years return period. So I will also try to show you how to ascertain or how to obtain the values of from the earthquake data, how to obtain the data for 200-year return period, 475 return year period PJ value for rock sites. Okay. Then it is mentioned that any settlement due to densification of loose granular soil, any settlement due to the densification of loose granular soils under design earthquake motion should be studied. Any settlement due to densification of loose granular soils under design earthquake motion should be studied. That means sometimes due to liquefaction, it will happen that soil will settle. So you have to take some measures to improve that ground also. Then the occurrence and consequence of geologic hazards such as slope stability and surface faulting should also be considered. But in Bangladesh, in generally, at fewer sites we have problem of surface faulting, like Madhupur fault site, then in Dauki fault, which is also sitting in the other side of the country in Indian part. But in Sylhet region, there are some sources of faulting, and Chirang region there are some surface faulting. But in most of the country, it will not find much direct surface faulting locations. But slope instability will occur in many places. So during those analysis, we have to consider all those things: liquefaction, settlement due to densification, and then slope instability issue. Yeah. Last point over here in this slide, the dynamic lateral earth pressure on basement walls and retaining walls during earthquake ground shaking is to be considered as an earthquake load for use in design load combination. So generally, Ronald sir yesterday showed you how to assess the K and KP, active earth pressure and passive earth pressure. But for dynamic lateral earth pressure, although in the code it is not clearly uttered, but you need to consider the Monobey-Okabe method. So if you Google it, you will find that there is lots of methods. If you know the seismic parameter like PJ value at the surface of any site, then you can use the Monobey-Okabe method to convert the K and KP value to Monobey-Okabe. That means for dynamic lateral earth pressure parameter, K and KP for dynamic issue. So the initial parameter like K and KP you need to know, and once you know the PJ value at the surface, using that one, using the Monobey-Okabe method, you can always estimate the dynamic lateral earth pressure parameters. So that is not also mentioned in the code, but globally, if you know at the surface level PJ value, you can always convert using Monobey-Okabe method. Okay, next comes site classification. This is also discussed, but again, I will discuss this because this will be required for this part of the presentation. The site will be classified as type SA, type SB, type SC, SD, SC, S1, and S2. Based on the provision of this section, classification will be done in accordance with table 6 to 13, based on the soil properties of upper 30 meters of the site profile. So over here, I will clearly mention that in many cases, although in many of these many countries, also in Bangladesh also, probably a couple of years back, people used to perform only up to 30 meters. That means the shear velocity they used to perform up to 30 meters. But sometimes you will find that VS30 obtained from 30 meters, because there is two methods to estimate site, as I mentioned, the site amplification or site response analysis. One of the method which is a little easier, if you can use the share of velocity, average share of velocity for the top 30 meter, you can directly use it to estimate the site amplification factor. But many of the times it has been found that the VS30 value obtained from the top 30 meter, average VS30 value obtained from the top 30 meter, not always present, not always give you the proper site amplification value at the surface. So sometimes for deeper sedimentation or sedimentation layers, you need to perform share of velocity up to at least share of velocity of 400 meter per second. So in Dhaka and in many regions, this layer exists up to 200 meter or up to between 200 to 300 meter depth. And in other regions, like in Podda Beach site or also Rupur power plant site, this layer, that means the share of velocity of 400 or more, exists below 120 meter. In Dhaka, it varies from 200 to 300 meter, but in other regions, it varies from depending on the location of the engineering bedrock. Because over here, if I go to the chart, I think you already know that in Bangladeshi building code in BNBC, the rock soil is defined as greater than 800 meter per second. But when we consider the engineering bedrock is defined for generally for residential building. Engineering bedrock is defined that it exists less than around 400 meter per second level. But if it is a power plant, generally it is defined that it generally is based on 600 meter per second, because real rock is very deep. So achieving the real rock, that means share of velocity of real rock, will consume a lot of time and a lot of investment. So sometimes the engineers do not go up to the rock. They prefer engineering bedrock, and which is defined in many classification and many reports all over the world. And for residential building, it is defined as 400 meter per second. And for important structures like power plant, it is defined as 600 meter per second. And some other structures like bridge and others, it is defined as the 500 meter per second. So there is some difference between the engineering bedrock and the rock defined in our code. Now, the following equation are generally used to estimate the average share of velocity. So we need to, when we estimate the share of velocity calculation, if we want to perform the share of velocity calculation from the share of velocity of the top 30 meter, we need to follow these three criteria. First one is for share of velocity, average share of velocity determination. Second one is the average SPT value determination, and the last one is the average undrained shear strength determination. And the site classification, the site profile up to a depth of 30 meters is divided into n number of distinct soil or rock layers. It is mentioned in the equation. But some of the layers, so it's just clearly mentioning that whether if there is some cohesive layers exist within the cohesionless soil, then how to perform that one. But it doesn't matter, because share of velocity, whether it is cohesionless soil or cohesive soil, you have to determine the share of velocity layer wise. Generally, we perform share of velocity or downhole method for each 1 meter, but in most of the time it is performed up each 2 meter level. But if you have the money and time, then you can perform each 1 meter. Then I think we can segregate the sand layer and cohesive and cohesionless soil layer, and we can average the value. The standard penetration value N is directly measured in the field without correction, and the average SPTN value, which has to be calculated using those equations, do not need any correction. That is what they are in the code. It is recommending. The site classification should be done using average share of velocity VS prime for top 30 meter. If this can be estimated, and if you cannot go up to 30 meter, there are other methods where they recommend how to estimate 30 meter from those other values. That means if your equipment cannot go beyond say 20 meter, then how to extrapolate up to 30 meter. There are lots of paper and lots of methods mentioned. So you have to search for the literature, but in the code it is not clearly mentioned. But there are literature from 20 meter. You can also estimate 30 meter share of velocity, extrapolating. There is some technique, and otherwise the SPT value N may be used. So say this is a case study where we have performed SPT value up to top 120 meter. This is for a power plant project in the northern part, and this is the profile where we can observe that for each borehole, and we have done a cross-sectional profile, and you can see the topsoil is very loose, medium dense, then density sand, and the whole soil layers are portionless soil. And then, since to perform site classification and PGA value estimation, we need to perform the shear velocity. Since this is an important project, we have also carried out PS logging for the site. And this is the picture of the PS logging, which we generally perform for determination of shear velocity. And over here, you can see the shear velocity has been carried out up to a depth of 125 meter. And at 125 meter depth, the shear velocity is around 600 meter per second. But generally for the engineering bedrock, we can perform just up to a depth of 400, that means where the shear velocity is 400 meter second. So although there is a thin layer here which is showing the 400 meter second, but we generally prefer a layer which is thick and continuously it is showing 400 meter second. So in this case, probably it is more than 80 meter depth. But still we prefer to go up to 600 meters since it's a power plant project. So we have carried out shear velocity up to a depth of 125 meters. Because for this site, we have carried out VS30 based site amplification, and we have carried out site amplification based on shear velocity up to a depth of 125 meters. And we have found out the VS30 based site amplification value is much smaller than the base shear velocity profile, using the 125 meter VS shear velocity profile to assess the site parameters of site amplification. So there is some difference. If we just use 30 meter, then the PGA value at this surface would have been much smaller than what we have used. That means the 125 meter, the total borehole data we have used for the site amplification for the one-dimensional response analysis. So from that we can see that there is some difference. Although some smaller project we can just use VS30. But for an important project, it is generally recommended to go up to a depth where the shear velocity is 400 meter per second for engineering for residential building. And if it is a more important structure like power plant, we have to go up to 500 meter or 600, depending on the importance of the structure. This already we have presented, but still I just want to show that the AC type, like we have to consider AC, S1, and S2. But we have to also see the SD type, because in most of our cases, we have found out most of our cities, the average shear velocity for top 30 meter generally is probably less than 80 meter. But for AC type, like SOL profile consists of a surface alveolum layer with base values of type SC or SD and thickness varying between 5 meter, 20 meter underlain by stiff material with base greater than 800 meter. It will be very difficult to find in our cities. But we have lot of sites where we have S1 type, like deposits consist of containing a layer of at least 10 meter thick of soft clays. Especially all our larger projects which are happening all along the coastal areas falls in S1 type. So whenever we perform any analysis or site-specific study for those sites, we need to be very cautious, and we need to perform the site-specific study. Okay, then if we move to the total historical earthquake studies, because in the BNBC, it is also there in the one appendix. It has been clearly mentioned that what are our historical earthquakes. But over here, just to show The major earthquakes in Bangladesh is basically the 1762 Chittagong earthquake, which also caused a tsunami in the Chittagong Arakan region back in 1762. That is one of the largest earthquake, the largest historical earthquake, which happened almost 250 years back. But this kind of earthquake generally occurred one in every 300 years. So since it happened in 1762, probably it will happen again, probably another 50 years later. But the smaller earthquakes like the 1869 Kachar earthquake or 1885 Bengal earthquake or the 1918 Srimangal earthquake or the 1923 Durgapur earthquake or the 1930 Dhubri earthquake, which are between or around 7 magnitude, this can happen in each 100 to 150 years. So return period for this kind of earthquakes are generally 100, 150 years. But all those earthquakes which are larger, that means greater than 8 magnitude, generally happens 300-year return with a return period of 300 years. Like 1897, so if we say that it is a 1900, it happened in 1900. So the next large earthquake, the probability of occurrence of this kind of earthquake is probably 2200. If we annotate, then sometimes the slides do not want to move. Okay. So these are all the large earthquakes in and around Bangladesh. So many of you, So many of you wonder that most of these earthquakes are lying outside Bangladesh. But if you see more minutely, you will find out that there are many, at least 10 earthquakes having a magnitude between 6 and 7, which are lying within Bangladesh. And most of these occurred long time back. So for the last probably 100 years, no larger earthquakes are happening in Bangladesh. But smaller level earthquakes, since we do not have any, why we do not have much earthquakes within our country is one of the reasons is we do not have any equipments. Although Bangladesh Met Department has installed probably 4 equipments in 2001, but many of their, I think out of those 4, at least 2 are out of order. So they cannot exactly pinpoint, like the Sylhet earthquake, recently Sylhet earthquake, there is no, how to say it, they cannot exactly pinpoint where the location of those earthquakes are. So we have to rely on United States Geological Survey, or we have to rely on Indian Met Department to identify to locate those earthquakes. So, but international level, if you search the database of International Seismological Center, if you also locate the USGS website, since we do not have any seismometer, or although we have 4 seismometer, but 2 are out of order, the smaller earthquakes which are happening within our country is not, how to say, measured that well. That's why, although we have some large historical earthquakes in our within our boundary, but the smaller level earthquakes are not shown that much. One of the reasons is since we do not have any seismometer or accelerometer, especially we need seismometer to locate earthquakes, those are not there. So at least we need 10 seismometers within our country to locate those. Like the Sylhet earthquake, which happened in a couple of days back, so we cannot measure those. Although people are saying there are 7 earthquakes, but Indian Met Department can only locate 2, and USGS could not locate at all. So we need some equipments to measure those, and for our future generation, so that we know what kind of seismic activities is happening within the country. So we have that lacking. So that's why the smaller earthquakes are not cannot be seen within the Bangladesh that much. So if we want to assess, so this data, like that means the earthquake data in and around Bangladesh is very important, because if we want to assess the seismic hazard of a location using the deterministic method, and if you consider the earthquake locations to be point sources, because we can assume earthquake sources to be point sources, we can assume earthquake sources to be line sources, we can assume earthquake sources to be area sources. But let's make it simple. If we assume that earthquake sources are point sources, Then if a site is located, say in Sylhet, first we have to make a circle within Sylhet, that Sylhet city. Say the location is, we need to assess the seismic hazard assessment for the Sylhet city. First, we have to make a 300-kilometer radius boundary from Sylhet and consider all the earthquakes within that zone. Okay. Then all those earthquakes has to be considered, and we need to make a kind of, how to say it, we generally call it seismic hazard at a site, bedrock, and we need to, there is two methods. One is the estimation of magnitude for this site, and one is estimation of PJ value for this site. So I will explain later, but I'm just showing these are the two curves we need to plot. The initial one is for estimation of the magnitude, and the second one is the estimation of the PJ value for that particular Sylhet site. So the first one, where we are considering or we are estimating the magnitude value for that particular Sylhet site, we have to gather all the earthquakes, as I mentioned, for within the 300-kilometer radius, and we have to make a correlation between magnitude and occurrence rate. That means we have to first consider, say, our database 300 kilometer, within a 300-kilometer radius, we have, say, 150 earthquakes. And within that 150 earthquakes, we have to segregate how many are between 3 and 4, how many are between 4 and 5, how many are between 5 and 6, how many between 6 and 7, how many between 7 and 8, and how many greater than 8. Then for each band, say for 400 to say we have say generally it is a customary, or it is general, the database always show that more smaller earthquakes, more are the number. Higher earthquakes has less number. So if say we have a 150 earthquakes within a radius of 300 kilometer, we'll always see that probably around 90 or 100 earthquakes will be between 4 and 5 magnitude. So if we consider that, if you see that what I have plotted is this diamond shape is in between 4 and 5. That means I have assumed all the earthquakes between 4 and 5. I said that I put the point as the average value on 4.5, and that 100 earthquake happened, say, from 1897, or our database is generally from 1870 to current 2020. So last 150 years we have 100 earthquakes. So the occurrence rate will be 100 divided by 150. So that point 4.5 will come from the magnitude, average magnitude, and that occurrence rate will come, 100 earthquake occurred in a time span of 150 years. So occurrence rate will be 100 divided by 150. And then again, similar way, if we want to calculate the average magnitude between 5 and 6, we have to again do the same math. That means say between 5 and 6 magnitude, we have earthquakes, say 30 earthquakes. So 30 divided by 150. That is the way. There are some other finer techniques, but I'm not going in details. But there are some techniques how to cut off. But for the time being, you just need to know for each magnitude level or magnitude range, you need to know the number of earthquakes divided by the total number of years. And then the similar way, we can estimate the average magnitude occurrence rate for range of 6 and 7 magnitude, and 7 and 8, and greater than 8. But we have said, since we don't have much earthquake between 7 and 8, so we put all those earthquakes greater than 7 in this way, so that we say that 7 and 5 is the value. So 4.5, 5.5, 6.5, and 7.5, these are the average value, and all those 150 earthquakes are distributed among those. And we have found out the regression analysis. I think most of us are basically engineers or architects or planners, so we know the regression analysis. So we made the regression analysis. Since it is a log scale, magnitude is x-axis, is normal scale, but occurrence rate, no, this is also no, but I think I made it in a log scale. It's written there. So the regression analysis will give you log nu equals minus, because since we have fitted that one, so it will be a straight line since the slope is negative. So that's why this a value is negative, minus 7034 into magnitude plus 3.623. And you see the R-star value is pretty high. So what is the importance of this regression analysis is, for any occurrence rate, you can get magnitude from here. Say I have a, we are calculating in our building code, it is mentioned that we need to estimate for 2,475 years. So if we put that 2,475 years means one earthquake in 2,475 years. So the occurrence rate will be 1/2475. So using this regression analysis, we can estimate the magnitude value. Similar way, if we want to make any liquefaction analysis for say 475 years, we can estimate magnitude value using 1/4. So for new value, we have to put 1/475 years, and then you can get the magnitude. So this is the way how once we have this regression analysis, we can estimate any magnitude for any occurrence rate. So that is the importance of this relation, and this kind of relation are generally called magnitude. It is generally called Gutenberg-Richter relation. It is devised or developed by Professor Gutenberg and Richter back in 1935, but it is still used. And the next correlation is for PGA versus log PGA versus log occurrence rate. Okay, so over here you see similar way, the y-axis are showing the similar occurrence rate, but x-axis is, instead of magnitude, is showing the PGA. But how to get the PGA value? To obtain a PGA, it is not easy, because you know Bangladesh do have some accelerometers, although it has only, as I mentioned, that instead of 4 seismometers, it has 2 seismometers. But generally for PGA value estimation, we do not require any seismometer. For PGA value, we need accelerometer. We used to have a couple of accelerometers in Bangladesh, but the thing is, we do not, as I mentioned, for the last couple of decades, we do not have much seismic activity. Although this year we are seeing a lots of seismic activity in the Sylhet and surrounding region. We have already recorded almost 30 earthquakes, but for the last couple of years we did not have much activity, and to maintain those accelerometers is very expensive. So we need to rely on some other laws which are called attenuation laws, which are developed for similar kind of situation. That means we need to find out some attenuation law which are similar in nature. That means similar nature of Bangladesh origin. That means the faulting mechanism, the other seismotectonics features which we have, those laws has to be for the similar situation. So Abram and Silva developed this kind of attenuation law back in 1997, which is developed for bedrock, which has been developed for a situation similar to Bangladesh and surrounding region. So it is very much popular. So most of our researchers who do this kind of analysis, they use Abram and Silva's attenuation law a lot. And using those attenuation law, we can estimate the PGA value for different locations. Since we have 150 earthquakes, we know the distance of those earthquakes from Sylhet region. We know the magnitude. Using those magnitude and distance, we can estimate PGA value in the rock, bedrock, using the Abram-Silva's attenuation law. And over there, since PGA value is PGA value can vary a lot. It can vary from 0.1 to 1000 centimeter per second square. That's why when you consider for magnitude, you can consider simple scale without any log. But when you consider the PGA value versus occurrence rate, you have to consider log scale, because occurrence rate also varies from very small to large value, and PGA value similarly varies from a very small to large value. That's why log scale has to be considered, and those has to be fitted. So over here also similar way, like 0.1 to 1 or less than 1, 1 to 10 or more other values, we can segment depending on the data we get. We can segment those, and 150 data has to be allocated for different band of PGA value. And then similar to the log nu versus magnitude, we have to again fit all those data using the regression analysis and those data are being fitted, and we can find out that log nu shom equals 0.456 log PGA minus 1.578. This is also a very high correlation value, although I have not shown it, but from the fitting you can see. And from this equation, for any occurrence rate, so occurrence rate may be 75 years, occurrence rate may be 100 years, it may be 475 years, we can estimate the PGA value for the sealant region. So this is the kind of seismic hazard for the site, for the bedrock. So this value which we can ascertain or we can estimate from this equation is only for bedrock, because Abramson's and Silver's admission law is related to bedrock. Okay. Next comes 2.5.4.2 seismic zoning. So in our code, it is clearly mentioned that the intent of the seismic zoning map is to give an indication of the maximum considered earthquake motion at different parts of the country. In probabilistic terms, the MCA motion may be considered to correspond to having 2% probability of accidents within a period of 50 years. So generally, the basic equation, I don't know whether I can write it or not. The probability equation, okay. Probability equation equals 1 minus e to the power, very difficult to control WebEx thing. I will write probably over here. Okay, probability equals 1 minus e to the power minus nu t. Okay, this nu is the occurrence rate. Over here, although it is mentioned 2% probability in a period of 50 years, this 50 years basically is t. This is this t. And occurrence rate, this nu is basically 2475 years. What is 2% of probability of accidents means basically 2475 years. Our probability is 2%. So if we put new value is 2475, 1 by 2475 and multiply with this 50, then you will get this value. And if you subtract from 1, you will get the probability value. So similar way, if we say that probability is 10% in a design life of 50 years, it means it is 475 years. If we put probability value of say 23%, it means it has a return period of return period of 200 years. So probability of 2% probability of accidents means 2475 years. If it is 10% probability of accidents, it means 475 years. If it is 23%, it means 200 years return period. But for a design life of 50 years, for the structure for which we are designing, we are assuming its design life will be 50 years. So for any return period, we can always convert to the probability of accidents using that particular equation. So the intent of, but in our code, it is clearly mentioned the intent of the seismic zoning map showing in our code is to give an indication of the maximum considered earthquake at different parts of the country. And in probability terms, this MCA means may be considered to correspond to having a 2% probability of accidents within a period of 50 years, which means 2475 years. The country has been divided into 4 seismic zones, as you know, from our seismic zonation map, with different levels of ground motion. And table 6.2.14 includes description of the 4 seismic zones, as you know, and figured the seismic zonation map figure showing the boundary of those 4 zones. Initially, back in 93 code, we have 3 zones, but in the recent code, we have divided into 4 zones. And also, we have subdivided some parts, which is in the southwestern part, in more detail, like the Punla area and the Shatk area. And each zone has a seismic zone coefficient Z value, which is basically the PGA value at the rock, which represents the maximum considered peak ground acceleration on very stiff soil or rock, which is classified as SA type in units of G, and it is expressed always in percents of G. The zone coefficients of the 4 zones are Z 0.12, zone 1, Z equal to 0.2 for zone 2, 0.25 for zone 3, and 0.36 for zone 4. But all of them will have be multiplied with a factor of G, since they are expressed with respect to G value. So you know, the previous map is for the 1993 code, although gazetted in 2006, but basically this map is developed in 1993, and this one basically also developed probably 2010, although gazetted in 2020. Okay, it is also mentioned already. We have mentioned that this table 6 to 14, and then the design response spectra. It is important because we need to estimate. These are although design spectra and other spectra are defined, but we need to modify if we want to estimate or if we want to develop the time history data for a particular site. We need to first identify which response spectra we have to use. And for this, that shearer velocity profiling or site classification is essential. Okay. So already these are discussed by Dr. Ghosh and others, like Z factor is that Z value importance factor are another issue. Just I will describe more detail how to. First, I will go into the response spectra curve. Then I can come back here. Then it will be easier to understand, because if you go there. So this is the basic, which is the typical shape of the elastic response spectra. And over here, site-dependent Saul factors are clearly mentioned. So TB, TC, and TD, these 3 factors for SA type soil, SB soil, SC soil, SD soil, and AC soil are defined in our code. But you can also using these equation provided in the code like 6 to 35, A, B, C, D, using 4 of these equations, you can also get those values. So because over here, Saul factor, which is provided in table over there in 6 to 16 are there, T of structure for that value is also provided over there. But using these 4 equations, you can estimate basically, and all these are only applicable for 5% damping. It's clearly mentioned because for structure generally we use or prefer 5% damping, and for 5% damping N value is 1. So N factor all provided in this equation we can assume 1, since we always use 5% damping, viscous damping for our structures. It is very common practice. So these 4 equations can be used annotate, then it is difficult. Okay, before going to develop the response spectra, let's see what are clearly mentioned over here. Site specific design spectra for site class S1 and S2. So specifically it has been clearly mentioned for site class S1 and S2, site specific studies are needed to obtain design response spectra. So for S1, if we get from shearer velocity profile and other parameter, if we know that our site falls in S1 or S2 site, then we have to perform site-specific study. Site-specific study means we have to perform seismic hazard analysis for the specific site, and we have to also perform one-dimensional response analysis for the particular site. This is the prerequisite. So for site class S1 and S2, we have to perform site-specific studies. And for important projects also, so 2 clauses. One is for site-specific study has to perform for S1 and S2 site, and for important projects, site-specific studies may also be. Here it is not clearly, it is not emphasized that much. I think Jonathan has explained to you what is the meaning of may and shall, but it is recommended for important project, site-specific studies may also be carried out to determine spectrum instead of using equations. Instead of directly using the equation, you also need to estimate the response spectra for this particular site. So for that reason, you need to also perform earthquake hazard analysis for that site and also perform the one-dimensional response analysis. The objective of such site-specific ground motion analysis is to determine the ground motion for local seismic and site condition with higher confidence than is possible using simpler, because in the equation of the code it's much more simplified. That's why they are mentioning that for important structure and for S1 and S2 soil, you need to make site-specific study. And for other structures, we can use the SASB, SCSD parameters, like S is the soil factor, and TBTC, TD is already provided in the curve below. That means in the typical shape of the elastic response spectra. And from this, we can get these 4 types of response spectra. But over here, you see the value given is normalized value. This value is normalized, like spectral response divided by PJ rock. That PJ rock will come from our building code seismic zonation map. But it depends. For not all structures, you can get you will use 2475 layers. Also in the building code, it is clearly mentioned that you can use 2x3 for DBA, design basis earthquake. But for some important structures, you need to also estimate PJ value for 475 years, because for DBA those values are much lower. So for some important structures like bridges and others, you need to estimate PJ value for 475 years, or what is mentioned in their design guideline for particular structure. Like for a nuclear power plant or for a important bridge like Podda Bridge, they generally use 475 years return period. For the railway link project, so for those you cannot use the PJ value to 475 years, or you cannot use 2/3 of those value for those important. You have to estimate PJ value for the rock for 475 years or other values recommended in those projects. Then you have to multiply with the normalized value, and then you obtain the SA value or SV value, AC value, because those sites classification are already defined in the shear of velocity, and using the VS30 value, you can estimate whether our site is falling in SA type, SB type, SC type, SD or SE, and then multiply those. Say our site falls in AC type, then you multiply that curve, which is provide normalized curve, with that PJ rock value, and you will get the response spectra for that particular location. But how to generate the time history for the location, that is not clearly defined in our code. But sometimes you need to obtain the time history data for that particular site. But basis is to obtain time history for that particular site. The basis is that curve which I mentioned, that you need to multiply AC with the PJ rock, will get the response spectra for the site, and using that particular response spectra curve, you need to generate the time history data. That is what is showing in this curve. There are lots of methodology, lots of techniques, and lots of softwares are nowadays available to develop that one. So over here, especially you can use, there is 2 software I think in the market available. One is earthquake risk software, I think developed by Berkeley or some other universities in USA, and there is also software called Seismosoft. Using that one, you can also use that one. So the target ARS, target acceleration response spectra, is basically that which I mentioned, that I have. We can estimate by multiplying the PJ rock from that building code curve, which is 6 to 26 for AC, and that one will be our target acceleration response spectra. And achieved ARS is we have to fit. So using the target acceleration response spectra, which is the middle one, and the upper one is the 1 + 1 sigma, lower one is the -1 sigma. The achieved ARS is the using the software, using trial and error. We have to come to the we have to obtain a response spectra which will match the target response. And in between, we will generate the earthquake time history. because to obtain a extraction spectra, we need to first we need to get the earthquake time history, and using earthquake time history, you can generate using FFT, fast Fourier transform, or other methods, or numeric beta method. You can generate the extraction spectra. So over here, to generate that particular extraction spectra, this is the time history, and when you match, these two are the showing. The black one is the synthetic time history, because using extraction spectra, we can use two methods. One is using synthetic time history. That means we can assume any parameter, and for our local soil, local fault mechanism, we can generate the synthetic earthquake time history, and then using the target, we can back. Again, there are other methods where we can directly use the real earthquake for very famous earthquake like Kobe earthquake, then Chichi earthquake, then Kokaili earthquake or Northridge earthquake, and then use that real earthquake to match the target response. So there is two methods. One is generating the synthetic earthquake for your own country using the fault mechanism, and also using the real earthquake data to achieve the target response. But both the methods ends in the same. That means you have to achieve the extraction spectra which matches with the target response. So this is the yellow color one is the match one, and that will be used for your modeling for building design. Okay, next comes dynamic ground stability or liquefaction potential for foundation soil. So in 3.9.5, because everything in detail, all the articles, but I think he has not touched upon this 3.9.5 article. That's why I'm trying to explain. So dynamic ground stability or liquefaction potential for foundation soils. Soil liquefaction is a phenomena in which a saturated sandy deposit loses most of its strength and stiffness due to generation of excessive pore water pressure during earthquake-induced ground shaking. So I think Jonas sir already explained to you the total stress and effective stress and generation of pore pressure in detail. I'm not going into detail, but just remember when the two precondition for liquefaction is the soil need to be generally, most of the soil need to be sandy in nature or questionless in nature. Second, water table has to be very close to the surface. These two are prerequisite for generation of liquefaction. For if you have a site where you have this condition, and if you think that earthquake will be significant earthquake will be generated, you need to study the liquefaction analysis. And also in our code, recent code, in this 2020 code, it is clearly mentioned for C and D type, you have to assess the liquefaction potential. So in the second point, it has been a major cause for damage for structure during past earthquake. Liquefaction is first experienced in the same year in two locations. First in 1964 Niigata earthquake, and second one is the 1964 Alaska earthquake. Both in the same year, one is in Japan, one is in USA. In both of those earthquakes, the researchers of those two countries were pioneer in liquefaction study and other earthquake study. They observed that liquefaction phenomena has occurred in both Alaska and Niigata sites. And you can see the top one, sorry, I don't know why. Okay. So liquefaction phenomena as a whole, you can see there is 4 pictures over here. One picture which is the top one, but top left, you can see one building slightly just settled down. One is slightly tilted, but if the liquefaction occurs beneath the site where a building is located, the building will not, there will not be any structural failure of the building, but building will gradually sink within the liquefaction. So same thing happens. You can see from the card, from the right below slides, the card has just sunk inside the soil. And in between, there are some other slides which is showing, one is probably in Alaska, the P point, and the C point is another location where the top one, you can see the road has subsided due to liquefaction beneath the area in Alaska. And the C point, C slides are showing a bridge with gas slides. And many of the locations, you can see one people is standing, and in liquefaction, what happens, soil behaves as a liquid. And the sandy soil, which is, behaving or showing very low shear strength, caved in. So you have to be careful that wherever you will find sandy soil, generally we obtain it near the river banks, where the recent deposits are there. And near the river, the water table is also very shallow. So these two conditions is prerequisite for liquefaction. So initially, if we do not have any money, liquefaction assessment can be done in many ways. So if you do not have enough money, you just try to collect data from the topography, and you estimate liquefaction based on just topographical survey. So based on that, it is clearly mentioned that areas with high potential to cause liquefaction, where the older river beds are there, and where the present river beds are located, as I mentioned, because those are carrying the alluvial silts and sands, and lowlands between dikes, sand dikes with high water table, and field lands, reclaimed lands. That means field land and reclaimed lands means if we fill any ground, most of our areas where we sell lands, like all the projects, government projects and private projects, like many projects in Dhaka city, if you go Google Earth and if you Google, you will see that lots of locations are showing white colors. Those are all potential sources of liquefiable areas, because those areas are generally filled with reclaimed sand from the using dry sand from the river. And the other areas like are less vulnerable to liquefaction, and terrace hills are almost negligible or low potential liquefaction. So areas with high potential is important to us, especially the older river beds, present river beds, lowlands between dikes, field or reclaimed areas. So if we have those areas, and from survey we know that, then we can say that these locations are potential source of liquefaction. So then if we have more money and if we have project money, then we perform more studies and perform liquefaction assessment. So the general most important liquefaction procedure is the provided by Professor Seed and Idris back in 1982. So they have observed in their literature, they have clearly mentioned over the last 25 years that from 1982 and backwards, a procedure termed as simplified procedure has evolved for evaluating liquefaction resistance of soil. This procedure has become the standard of practice in North America and throughout the world, throughout much of the world. Still, we are using it, one of the methods. But when we use one method, it may be sensitive to some parameters. So generally, for liquefaction analysis, we use 2 to 3 methods to compare different methods. Generally, 3 methods are very popular, although we will describe here Seed and Idris method, but you need to know also there is one method by Japanese societies, soil mechanics, foundation engineering, and one other method is proposed by Chinese researcher, which is called Chinese method. It is also in their code. So generally, when we perform liquefaction analysis, we always compare 3 methods: Seed and Idris, Chinese method, and the Japanese method. So one is US based, one is Chinese based, and one is Japanese based, because these 3 countries has more prone to liquefaction because they have more earthquakes than other countries. So this procedure has, so although I'm showing only one method, but you need to, when you use in the real world for consultants or any other projects, you always need to compare 3 methods. So you know the sensitivity or the limitation of the other methods also. So this procedure has become the standard of practice in North America and throughout much of the world since it is US method. Following disaster earthquakes in Alaska, Niigata, 1964, Professor H.B. Seed and Idris developed and published the basic simplified procedure. The procedure, which is largely empirical, evolved over the decades primarily throughout summary papers of H.B. Seed and his colleagues. And over here, they clearly mention and they clearly estimate the factor of safety of liquefaction, which is called factor of safety for liquefaction potential, R over L, where R is the in situ resistance of soil. That means R generally expresses the capacity of the soil to resist liquefaction, which is sometimes called CRR. And L is the earthquake load induced by a seismic motion, which is defined by CSI. And if the factor of safety FL, that is F subscript L, is less than 1, the liquefaction is said to take place. Otherwise, liquefaction does not occur. The factor of safety obtained in these ways is generally used to identify the depth to which liquefaction is expected to occur in a future earthquake. This information is necessary for if countermeasures is to be taken in an in situ soil. That means if you can estimate liquefaction for a site and if you have a liquefaction susceptibility, then you have to consider some soil improvement measures, because our assessment is showing the site is susceptible to liquefaction. So when the future structures will be built, it may settle. So before before those can happen, we have to improve the soil so that when in future the earthquake occurs, the soil is improved sufficiently so that the structures remain same. There is no collapse, no settlement of the structures. So this is the issue. So in more detail, to illustrate the influence of magnitude scaling factor, also magnitude has a significant effect. And although I'm showing one equation for magnitude calibration, but there is numerous equations for magnitude calibration. But in the CD&EDRIS method, they are showing that for a magnitude of 7.5, the MSF value is generally considered to be 1. But if the magnitude is higher, MSF value is lower. And if the magnitude is low, MSF value is higher. So that means less liquefaction susceptibility. So CD&EDRIS also proposed for CSR, that is for dynamic load, 0.65 into Amax. Amax is basically the surface level PGA value that you have to estimate for a site, because in the building code it is not mentioned, it is not there, because the building code is saying PGA value for rock for 2,475 years. But for Amax, which is the PGA value at the surface, you have to use some technique, site-specific study or some other methods to obtain the PGA value at the surface. G is the extraction due to gravity. Sigma V0, you already know total stress. Sigma V0 is the effective stress. RD is important, which is some reduction factor. I will show you later how to estimate that one. So RD value, generally, Professor CD&EDRIS has given a different, RD equation, but over here, it has been taken from some recent study, not recent, but back in 2001, there is a workshop with different very famous people gathered together, and they have convened a workshop, and they have decided that these are the equations, these are the things we need to do. That means they have improved Professor CD&EDRIS matter, simplified procedure, and it is called NCER. And they developed in 2001, and they proposed that it is better if Z value depth is less than 9.15 meter, we better use RD value, that means reduction factor 1 minus 0.005765. And then if Z value is between 9 meter, 9.1.5 meter to less than 20, then you use this one, and that way. But generally for liquefaction, it has been observed beyond 20 meter, due to the high overburden pressure, probably there is very few locations where liquefaction occurs. That's why liquefaction study we generally perform up to 20. So from this figure, you can see the BNBC, they are providing the PGA value at the base, and we need to estimate the PGA value at the surface. And for that, you need to know a lot. You need to the soil layer properties, you need to the location of the water table, and many other parameters are required. But important thing is, one important thing, I think probably all of you know, but just to mention, generally you see that this factor 0.65 is important, because Amax value which we get from the time history data is pretty high, and it is probably generally 1 pulse. But the other mx value or other PGA value, other acceleration values or acceleration values are generally much smaller. So it is a reduction factor to reduce the mx value, because otherwise the PGA value obtained in the surface will be much higher. But since it is not sustained for the whole time, as you can see from the figure, you can see that there is only one pulse here and not sustaining for the whole time period. So it is better to reduce the PGA value using that factor of 0.65. That's why that factor. And okay, so that's why site response analysis of a site may be carried out to estimate the site amplification factor. That's why to obtain the bedrock from the bedrock to the surface, that means surface PGA value, you need to carry out the surface amplification factor, or you need to perform for this purpose dynamic parameters such as shear modulus and damping factor need to be estimated. The site amplification factor is required to estimate mx value. So to estimate the, although I'm saying that site response analysis need to be carried out, but it is not an easy job, because you need to also estimate the dynamic parameters like shear modulus and damping value. And but interesting thing is, all over the world, so much research has been carried out and so much curves has been generated for sands and clays for different countries, that we can always use that, because to generate and develop our own dynamic parameters for shear modulus and damping will take a lot of time. Although for two sites, for Podda Bridge site and for nuclear power plant site, we have generated those, but it took a lot. And each of those sites has also allowed us to provide master's degree for one student. For Podda site, one student, and for the Rupur site, another student, because so much data has been generated to develop those dynamic parameters that you can give such a degree, because so much research need to be done. So, but for our case, generally, if we do not have parameter, generally all the software which we generally use, they have those curves inbuilt, and you can use those, no problem, because sand, and although there will be some changes if you want to do some surface study, but to get those dynamic parameters is a cumbersome job and time consuming. So for very important structures like power plant and like very important nuclear power plant or bridges, long bridges, you can do that. But for other structures where site-specific study is required, you can use already established curves, dynamic curves like modulus versus strain, damping versus strain curve, already provided in the software. Then again, you need to provide the layer-wise data like shear velocity, density value for all the layers, and then perform one-dimensional response analysis. And if you provide those one, you will get surface level PGA value for the particular site which you will use, because PGA value at the rock site will be generally, in most of the cases, is generally amplified. Sometimes it is de-amplified, but in most of the cases, it's generally amplified. And if we put an input value of 0.15 G, it will be around 0.27 G or sometimes 3 G. So it is also showing here, since we have input 0.15 G for this particular site, it is increased to 0.27 G. So PG value at the rock is 0.15, PG value at the surface is 0.27 G. And using that 0.27 G, we need to perform the liquefaction step. Okay. Okay, the second step is to determine the cyclic. So we discussed the loading, and now the second step is to determine the cyclic resistance ratio of the in situ soil. The cyclic resistance ratio represents the liquefaction resistance of the in situ soil. The most commonly used method for determining the liquefaction resistance is to use the data obtained from the standard penetration test, because it is a very common. Professor Idris developed that one, and later on, as I mentioned, back in 2001, NCER report has combined and enriched that one. For nuclear power plant, we need to manufacture test earlier, but it's a very cumbersome process. It took a lot of time, almost 6 months to develop. Test is not a very time consuming, but to gather the data and to process the data is a very time consuming. So generally, most of the cases will prefer SPT value, but very important structure, as I mentioned, for power plant, nuclear power plant or bridges, we can do cyclic reaction. But in general case, we either use SPT based or CPT based. And for fine grained soil, I think in the equation provided in the building code, there is some mistake. So just before before the presentation started, one of my students, he just rang me and showed that there is some mistake. So, but we do not use that much because although it is shown that in the code, they mentioned that Professor Finn has mentioned that if the soil is finer than 0.005 and its percent is less than 10%, fine content is less than 10%, then the soil is susceptible. A liquid limit has to be less than 36%, and natural water content and both liquid limits, these should be greater than. In the code, I think there is some mistake. They showed that it is less than 0.9 and 0.75. So probably we need to also correct this one in the code in the later stages. So the simplified base curve for clean sand is basically this curve, which is provided by Professor Sid. So this is the base curve provided by Professor Sid, and it is back in 95. So after 1982, they have improved that one. But in 2001, these curves are from the 2001 MCR report. So what they did, together they have together all the big professors in US sat together and they said, because Professor Sid and Idris's curves is made in such a way that it is supposed to go through the 0 point, but all the workshop participants say that it should go in through this point, which is 0.05. And another thing they have added is they state that for other soils like not clean sands which have some kind of fine content, they say greater than 5%, greater than 15%, between 15 or 35 and greater than 35%, we need to follow some other lines. And those lines are shown here and also shown in some equation in the later part. Let's show you. Okay. So these are some changes. So correcting SPT value for CT sands to an equivalent clean sand, because we'll have more pure sand or clean sand. That's why for CT sand, you have to increase the SPT to take care of that issue. That means increase of the resistance value. So that means more SPT value, more resistance. That's why in that particular workshop, all the researchers together, they provided this equation that N160CS, which is the corrected for other than clean sand. Alpha is the factor which is dependent on the fine content, and beta is another factor which is also dependent on the fine content, but it is a kind of correlation curve. And alpha value is 0 for less than 5%, alpha between 5 to 35%. The equation is provided here, and if alpha fine content is more than 35%, so you have to increase the SPT value by 5. And also beta value has to, that means N value has to be multiplied with 1.2. So that means much higher SPT value. Say if a SPT value is 10 for clean sand, it will be 17 for fine content having a fine content of 35%. Okay. Then comes Professor Yasaki's method back in 82 and 84. It is a suitable method because Professor Sedan, in this method, it only mentions liquefaction potential for a particular layer. Generally, we estimate liquefaction susceptibility for each 5 feet or 1.5 meters. But if you want to know the liquefaction potential of a whole borehole, you need to know liquefaction potential index up to a depth of 20 meters. And Professor Dr. Yasaki, in his numerous papers, he published from 1982 to 1986, he published several papers. One of these, the last paper was published in Soil Dynamics and Earthquake Engineering back in 96. And over here, the 82 method, which is clearly mentioned in the initial method, the liquefaction analysis by means of liquefaction potential index defined by Yasaki et al. Is different from the simplified procedure of the Sedan-Nittis method. It is definitely because Sedan-Nittis always has clearly mentioned this liquefaction susceptibility for a particular layer of each 1.5 meter. But Yasaki defined the simplified procedure predicts what will happen to a soil element, but the index LPI predicts the performance of the whole soil column up to a depth of 20 meters. The constants of the liquefaction at the down. That means if you want to make a microgeometry map for a city, if you want to study for the whole site altogether, you need to know for the whole soil column up to a depth of 20 meters. That's why Yasaki's method is very popular and very simple. That's why, furthermore, the effect of liquefaction at depths greater than 20 meters is assumed to be negligible, since no surface effects from liquefaction at such depths have been reported by different researchers. So, Yasaki's method proposed is LPI value. It is a summation from FW. It is not same as FL from 0 to 20 meters. Over here, generally the W value, because in the equation you see that there is two parts. One is FW, one is DZ, that is the each thickness 1.5 meter generally we can take. One is F value, one is WZ, one is DZ. DZ is fixed 1.5 meter for each 1.5 meter. F will be dependent on 1 minus FL, I will come to it, and WZ is always again another factor which showing the depth factor. So Yasaki clearly mentioned the depth weighing factor WZ equals 10 minus 0.5Z, where Z is the depth. The weighing factors over is Z when Z is 0, WZ is 10. When Z is 20 meter, WZ would be 0. The variable Fs, which is the key component, which is dependent on the FL value determined by Sedan-Nittis method or any other method, is saying that 1 minus Fs. This Fs is basically susceptibility factor or liquefaction susceptibility factor defined in Sedan-Nittis method. So when Fs is less than 1, F will have some value. And when Fs is greater than 1, F will be 0. There is no liquefaction for that location. Okay. And Yasaki defined and classified LPI value in 4 parts basically. One part is high liquefaction when LPI value is greater than 50. When LPI value is between 5 and 15, it is called high liquefaction. When it is generally, although he mentioned less than 5, but generally we most of the researchers classify it from 0 to 5, because LPF equal to 0 is the lowest criteria, but the third is low liquefaction potential if it is between 0 and 5. And if it is 0, then it is the very low liquefaction. So 4 types, although in 84, Professor Yasaki classified in 3, but most of the researchers use 4 types. Another type they have added LPI equal to 0. Okay. So this is a particular site. I have already showed the soil layering previously. For that particular site, we can see using the simplified in this method, from this point up to this point, there is liquefaction because it is less than 1, and other location, that means above 2 meter and below 10 meter, almost there is no liquefaction, using simplified. But for this particular site, we have used simplified in this method, then Japanese method, as well as Chinese method. And 3 methods are little different because we need to study the sensitivity using different methods. But using the simplified method, we can see if we use the USX method and classify into 4 types, we can see most of the, since this site is located very close to the river, and most of the site up to a depth of 120 meter is sandy soil, although beyond 20 meter the soil is much better, that is more dense. Topsoil, there is very loose soil, so soil liquefaction is very high. Even considering a PJ value of for 475 years, this is not even 2475 years. This is considering a PJ value of 475 years. So site response analysis has been carried out, and PJ value is around, I think, 0.23 G for this particular site. And you can see probably around 30% or 40% of the site is very high liquefaction. Then moderate liquefaction is, I think, another 65% and 5% probably low liquefaction. And there is almost very low liquefaction, there is no location. So this site is very high, on average, very high liquefaction. Or we can say not very high, high liquefaction. Since there is some 30 to 40% very high, but most of it are probably high liquefaction. So we need, if it is a power plant site, we need to improve the site because important structures will be installed. And even we design pile, still we need to make, because pile will be higher than, deeper than 20 meter. And we have seen in one of the large earthquake in Bhuj, even a 20 meter deep pile has inclined 15 degrees in the Kandla port, whereas the soil water table is very high. Over here is also water table is very high since it is located near the river. And then together with the pile, you need to also improve the topsoil. So soil improvement has to be done. Just piling will not save you. So liquefaction assessment is important because just putting pile will not give you the full coverage against liquefaction. Okay, what are the remedial measures? In Bangladesh, we are lucky because recently for the last 5 to 10 years, we have undertaken so many large projects. And we, especially from Bhuj side, we are also lucky because we are involved with almost 90% of these projects. Like for the bridge project, Rupur power plant project, we have some projects along the coastal areas, which are very important projects, and we are seeing lots of soil improvement. And as Dr. Ghosh has also mentioned that we have carried out also detailed engineering assessment of numerous garment industry. And over there, we have found out they have put, especially in the coastal areas like in Chittagong, EPZs and CEPZ and KEPZ, they have some structures where they have high-rise buildings and they have put piles. But we have estimated that since Chittagong area is very vulnerable to earthquake, the high earthquake will not save those areas. So we have carried out assessment both for soil and buildings, and we have also taken soil improvement measures in those sites. And I will just share some of them. So, but overall, in the mechanism of soil improvement or remedial measures, generally 4 types of measures are taken. First remedial measures is soil improvement countermeasures. So if your project is, that means the building is not very tall And if you do not have very deep soil, then just locally you improve the site, and it is the soil improvement technique. But as I mentioned, for a little higher structure, like a little high-rise building, say 10 to 12, even you put pile, you still need to improve the soil. It is not my saying, it is defined by Ishumi and Sasaki, the Japanese researcher or professors. They have undertaken many researches and they have compiled this one, these 4 pictures. And if the structure has several basements, you can remove the, say if a structure has, say, 3 basement or 4 basement, so you can go deeper. So if one basement is, say, 4 meter, so if you have 5 basement, you can go deep as 5 meters. So you can remove the liquefiable soil and you put the basements there. So super high-rise building, you can do that. And fourth one, this is important. Sometimes if you do not improve the soil, you can what you can do, you can locally improve the soil and you can confine it so that the water cannot go out or go below. So we have done it for one of the projects, so it is still surviving. So although there is no large earthquakes, but these are the 4 techniques. First one is the soil improvement technique. Second one is the pile, including soil improvement. Third one is nothing, but you have to put deeper basement. That means you have to put more and more basement. So it is feasible if your structure is super high rise. And then the other one is the confinement, because if you do not allow water to go out from the soil, there will be no settlement. So in Japanese practice, they use a lot of sand compaction pile. In Bangladesh, all the recent projects we have done, we have undertaken dynamic consolidation technique. Especially if I mention 2 projects, we have 2 very important projects, but people have forgotten. One of the very old but very renowned projects is projects of one of our very old power plant, which is located in Ashuganj, I think, in Ashuganj power plant. Yeah, Ashuganj power plant, which has been commissioned by the Russian back in 1979. So during that time, Professor Jayat Chaudhary and his team developed the second seismic generation map for Bangladesh. The first one was developed in Pakistan period but published or gazetted in 1972. And then the second one was published in 79 based on Indian seismic code. But their 79 code is a little different. It is not the PJ value. It has some factor. It is called seismic coefficient factor. So you cannot directly compare this 1970 seismic generation map with the new one. But that one is important because for Ashuganj project, they used it. And they found out with some calculation that for Ashuganj site, the PJ value is 0.2 G. And when they improved the soil, they used 0.2 G, and they needed to improve the soil. And the first important projects in Bangladesh where site improvement has been carried out using dynamic consolidation or heavy wet tapping. In dynamic compression, generally they use 20 to 40 ton load, and they drop it from a height of 10 to 20 meters several times, and they improve the whole lot. So in a new projects, recent 2 projects, we are also using dynamic consolidation, and we are also using grouting, jet grouting technique, especially in Rupur projects and especially for building projects like the RMG sector. So in Bangladesh, I think we have now dynamic compaction technique. People are using it. We have PVD. Although PVD is not used for liquefaction, but dynamic compaction and jet grouting is very much used for liquefaction potential index and sand compaction. But sand compaction is not suitable much for big area. Sand compaction is more important if the site soil is, you can say that has some clay soil also. Although Japanese researchers use sand compaction a lot, but in Bangladesh we preferred, and we have already used sand jet grouting and dynamic consolidation. I'll show some pictures. Although sand compaction pile is popular in most of the railway projects. Some railway projects in Bangladesh, they are using PVD together with sand compaction pile, because those are viable, especially if the soil is, how to say it, okay, if a soil contains organic content, so sometimes PVD is not feasible, then together with PVD, you also need to perform sand compaction. So in many rail projects, they are using it. And also in some of the projects where flyover are being built, especially there is a new flyover in Kalshi area. Over there, Abdul Monin Limited has imported a sand compaction pile, and they used it for soft soil purpose, to improve the soft soil over there. So using ground improvement using jet grouting method, jet grouting is a technique which is very suitable for sandy soil to improve, because through jet, what they do, they push cement with water with a high pressure. And since cement is a finer content than the sandy soil, what it happens, the small pore spaces between sand are filled with cement. And automatically, a very strong, how to say it, cement mix mass of sand are developed, where after testing, we have found that concrete strength is quite high. Why I'm saying concrete? Because once they make, like, there's 4 pictures you see. I wanted to show video, but I think in Webex video is not allowed. That's why I have to explain through that one. But 3 steps are there. The first step, you see the jet grouting are put in a deeper layer, and then from there, okay. So say our target is 20 meters, since 20 meter is the depth up to which liquefaction may occur. So first they put the probe at a depth of 20 meters. Then from there, there is 3 ways to perform the jet grouting. One is how to say it? How to say it? One is just pushing cement directly. One is mixing cement with water. One is mixing cement, water, and air. So most popular is mixing cement and water. But better performance is sometimes if we mix water, air, and cement performs better. But in Bangladesh, the 2 machines we have, or 3 machines we have, can push water and cement together. And what happens, once they reach the desert depth of 20 meters, gradually we can increase or decrease the pressure of the cement ground. And depending on how much we need to improve, we push cement with water, mixing with water with high pressure. And gradually we go up. Gradually we go up, improving the soil side. I will show what is the size of the soil column and how it improves. So see, the first it has been done, second it has been done, and middle. So this is the 1, this is 2, and in between they have performed this one, so that this total soil area is covered. In especially as I mentioned, when RMG sector, they have used jet grouting, because jet grouting can also be done inside, from the inside the building. And one of the factories in Akij, where there is some settlement problem, they have also used jet grouting to improve the local soil. And currently we are using for large projects in the coastal area. Okay, so this is the okay, this is the jet grouting technique. Although we cannot see anything, but there is 3 pipes, because at the same time they are running 3 pipes instead of 1 pipe. They are running 3 pipes, so that at the same time 3 how to say, 3 columns, soil columns are generated, and they have done it. The Chinese can do very good thing with a very cheaply, and they have improved. And you see, these are the silos where cements are there, because generally for these are cement silos. Generally for cement you need OPC. OPC is preferred over other cements for cement grouting, jet grouting. we annotate, then sometimes it hangs. Okay. And then after they completed the jet grouting, we asked them to uncover below the ground level, and they have found that these are the soil columns. Okay, and then they measured the cement columns. Generally, depending on how much we need to improve and how much pressure we put, generally we can make 24-inch column, then we can make 40-inch column, depending on high pressure. And then we need to perform the core test. We need to perform the core test to know the unconfined compression strength of the soil mass after improvement. Because we have some criteria, and following that criteria, because otherwise there is no way. So we always collect cores from at the middle. We make a core in the middle of the column, improved soil mass, or we call soil column or jet column, and we take cores up to the desert depth. So generally, sometimes we take, because for not all the columns, but some of the columns we take up to 20 meters. So to know the quality up to the whole soil mass or improved mass. And then we test, and we know through the unconfined compression test the strength. And these are the cores collected from that particular site, and we have checked it is sufficient. The quality of concreting using cement grouting is sufficient for this particular site. Then we perform, depending on the location and depending on the, because this picture is also similar to what we have carried out in our site, and we have the left one, right one side. Right one is showing our site, and left one I have collected to show because I don't have any aerial picture for our site, but it is similar to this brick, but locally fabricated. So you see, they have done the dynamic compaction at a regular interval. So after completing that one, again they will do another one in the middle, so that whole area is covered with dynamic compaction. So they do 4 to 5 times. Then they fill the area, that means the mass which is the settled area, they fill with sand again and again compact. Ultimately, they fine tune it using vibratory roller. For big area, dynamic compression is very popular and very cheap. And also our one of the important projects where dynamic compaction, PVD, both of them has been carried out is a project which is located below our MRT depot. And they have spent a lot of money over there, and they have improved using this soil in Uttarakhand. And this is the way you see the soil mass being dropped from certain height, but where the equipment will be put, the work platform has to be very strong, because the equipment itself is very heavy, because it need to have a counterweight more than 40 ton if we want to drop 40 ton from a certain height. And generally the soil area is improved up to a certain depth. But generally, as I mentioned in the previous table, you see approximate applicable depth is 10 meters. Generally, it is soil improved by dynamic compaction is generally up to minus 10 meters, where the soil is poor up to that level. Okay, then how to evaluate? How to get that, or how to know that our soil which we are getting is better than which we have previously. That means we need to know the soil condition beforehand and soil condition after the improvement. Otherwise, we do not know how much it has improved. For this particular site, we have performed CPT, because SPT is sometimes we do, but SPT is very much human dependent. It has some error, and sometimes if you want to make comparison for each 10 millimeter, because CPT is very precise and CPT does not have any human interference. It is fully computer oriented. Data is all recorded within a computer, but SPT is always human error there. So what we have done CPT. The red color one is before improvement and green color is after improvement. And we can see up to a certain depth, it has improved. And again, what happened, since we do not rely on CPT alone, and we have a requirement that after the ground improvement, the bearing capacity has to be more than 80 kPa. We also conducted, probably you already know, we have already conducted plate load test over here using 1 square meter size plate, a large plate having 1 meter by 1 meter size. And after confirmation, we have found out that our site has improved sufficiently. And you can see from the test plate load that our target is 80, it has reached 160. So if we divide with a factor 2, we can get 80 kPa. So it is satisfied. The plate bearing plate is 1 meter square, so it is a very big plate, 1 meter by 1 meter. Generally, we use in our country 1 feet dia, but it is not sufficient. It is better to use more larger plate, use more reliability. Okay, so far I tried to present it whatever I tried to do, but now the floor is open for question. I think there is a lot of question over there. I was observing that there are many questions, but okay, I will try to answer those. Let's see. Let me go. Almost 36 questions are there. I don't know whether I will be able to answer all of them. The first question is, since most cases in our country only SPT tests are to be conducted in the soil test, then we calculate the undrained shear strength and shear wave velocity from this SPT results or value, then will the code allow this, or is it compulsory to conduct undrained shear strength and shear wave velocity test from the field? Generally, if your project do not allow, or if your project does not have enough fund beyond SPT, then you can use SPT to convert shear wave velocity. But the problem is, in Bangladesh, we do not have any reliable relation between SPT and shear wave velocity. First, we need to develop those, and then you can use. It's better to develop those one, then use it. But unless and until we have it, then we can use some other correlation. But we need to be very conservative. That you have to remember. But in Bangladesh, I know currently at least we have around 10 PS logging equipments. So I think it is available, and I think it is now become very cheaper. But for SPT, but probably you already know that for clay soil you cannot perform SPT. You need to perform undrained shear strength in the lab. You have to collect proper undisturbed sample and then perform. So if you do not have any other measure, then SPT, you can use SPT. But you have to be very careful. You have to make some sensitivity analysis. You need to use several correlation to check. And probably it is better to use a conservative value for your analysis. So this is the first answer. You can use SPT if you do not have any other means. Okay. Second one, Rifat again. You have any good reference or sand compaction piles? I think Masaki Kitazume's book is the only one. It is, you can call it is a Bible for sand compaction pile. Some of my students have used it, although it is a tricky to use it. But you can also have some case studies. You can download some papers of case studies, but I think Kitazume's book is the most famous, and it is very comprehensive, but a little difficult to understand sometimes. I don't have any other reference except that one. And for liquefaction potential analysis, would you please suggest a best reference? As I mentioned, for liquefaction analysis, you have to use at least 3 methods to compare, because one method will not give you satisfactory results, or it is not. I will not suggest that use one method, because, as I mentioned, that those methods are very empirical. These relations are empirical, not 100% reliable. So if you use 3 methods and those 3 methods indicate the results are similar, exactly 100% similar result you will not get, but similar type of results, that when liquefaction potential is high for all those methods. So it is better to use 3 methods. to arrive in a good conclusion. Then Rifat again, if you create a or dug a pit nearby the building foundation to help in percolate rainwater into the ground, think it would be adverse effect in long or short term of the foundation or not? Pit nearby the building foundation help percolate rainwater. But why you need to percolate rainwater? Because generally I think if the soil is clay soil, I think water will not play a major role. But if it is sandy soil, probably already you know that using a correction factor, if the water table is in the ground, bearing capacity will be halved. So you have to be very careful. If it is a sandy soil layer, it is better to improve the soil so that water does not play a major role. It's my view. If again, is it required to calculate lateral capacity of both piles in sandy soil or not? It is required, and probably there is STM method also. I think Jonas sir has mentioned 11, 14, 43 for static, but also you need to for lateral capacity of piles, board as well as other piles. There is, I think, number I forgot, but I think 5266 probably. STM 5266 is for lateral pile capacity estimation. And we have done it for several projects for estimating the lateral capacity of board as well as driven piles. Rifat again, is longitudinal reinforcement of column bars oriented toward the center of the column in foundation are better than outward or center of the column? It depends, but you have to make good connections with the pile cap first. That means the pile cap rod and the rod coming from the piles has to be properly connected. And then rods coming from the columns need to be properly connected with the pile cap so that the whole thing is work as a monolithic structure. So during earthquake, it behaves as a monolithic mass. Some reference books which help us to calculate lateral load. I think there is several books. There is one handbook on foundation design. I think I forgot the name. 10 or some Chinese author, and also book by Paulus and Davis books are there to calculate, I think, the pile capacity both vertical and lateral. So you can use for pile you can use Paulus and Davis book. Then Habibul Hasan. Okay. I don't know. The question answer thing is not going down. Just let me check.
Professor Ansari, can you you can click on a question and then use your arrow.
I know that, but sometimes the how to say it, scroll bar is not going down. That's the problem.
Oh, you can use your arrow going on your keyboard. Highlight a question. Click on a question and then use the arrow in your keyboard going down.
Oh, okay. Yeah, thank you.
Is it working? Okay, good.
Yeah, it's okay.
It's okay.
Not always is going down. Okay. Then Habibul Hasan, tie beam and foundation slab is required to connect to pile cap or footing level. Does grid beam connected with column in both main direction serve as tie beam? You can use. Sometimes grid beams are also used. So over there it is clearly mentioned, tie beam or foundation slab, or sometimes grid beam can also work. Grid beam has to be provided to stop the differential settlement, definitely. What is the bearing capacity value for loose sand or medium sand or dense sand, stiff clay or medium clay or soft clay? It helps to estimate the judge the value. It is a very vague question. It is not very clear because what is the bearing capacity value for loose sand or medium sand, stiff clay or medium clay? It helps to estimate and judge the value for checking. I don't know what is this question is exactly for, because it is a very broad question mentioning sands and all types of clay. If you mean, because as I mentioned, bearing capacity for sand is very tricky, because for sand you need to always consider the water table. For clay you do not need to consider that way. And I think Jonas sir has also shown you lots of equations to estimate the bearing capacity. And if grade beam does not serve as tie beam, I think it is already give you the question. I think sometimes you can use grade beam to restrict the differential settlement. So the building is standing for 15 years without showing in distance, but calculation based on soil test report shown that factor of safe of shallow foundation is well below the allowable limit of BNBs. In this situation, what type of soil insulation is required? Such as traction, definitely traxial drain test, because many of the garment industry, we have done that one, and using drain traction test or sometimes drain direct shear test, because sometimes traction test is expensive and takes time. So instead of traxial, we also perform direct shear drain test, and we have got better results. And using those parameter drain test, bearing capacity becomes much improved, since both C and 5 parameters are there. When and how we can consider fixed support of the column, foundation joint, or auxiliary footing, custom modeling can explain. Generally, for deeper foundation, we generally assume for pile foundation generally we fixed condition, and generally but it depends on many other parameters. But generally, as I mentioned, probably for pile foundation you can assume fixity. Etesham, how to design pile foundation near liquefied soil? As I mentioned, the normal design, but you need to improve the local site for the top. Say if a 20-meter site, if a pile is put for top 20-meter, at least up to 6 meters you have to improve to give the fixity, because if the soil is fully liquefiable, the pile will act as a slender column. So it is better to make, because the bottom is strong, but top surface you need to also improve so that slenderness is lower. That is the way. Where can we find the time history data of earthquake support? You do not need to find. You can use, as I mentioned, you can use, because we do not have earthquake data in Bangladesh that much. As I mentioned, although we have some equipment, although we have put the equipments back in 2003 in Jamuna Bridge, but we have not recorded much earthquake, because we are maintaining the equipment still. But recently, Jamuna Bridge Authority has cut the funding. They don't have any fund. We cannot maintain it, because last 20 years we are maintaining, but we do not have any earthquake. But recently we have some earthquakes, but equipments are out of order due to lack of maintenance. But so what we use, as I mentioned in my presentation, it is better to use historical earthquake all over the world, important earthquake all over the world, and use our response spectra and use our bedrock value to generate our own time history. That is the way, using the matching technique as I described. CPT based technique, because building code, if you want to put all the techniques, like Samuel said, why no provision of CPT? Because CPT is mentioned over there, but not detailed. Because as I mentioned, and also Jonathan yesterday was saying, I was listening to him, that it is not possible to put everything there. Because if you want to put all those things over there, building code will be vast. So you have to use your judgment, and if your project has sufficient funding, then you can perform CPT and you can perform two tests. As I mentioned, if you have enough funding, you can perform SPT, CPT, SCPT, and both, and also as well as PS logging or downhole method. Okay, then another question by Asan. If any factory stands for 10 years without showing any sign of distress, but based on soil test report, the calculation shows the factor of safety below the NBC level. Now, retrofitting, we do not generally allow retrofitting to occur that easily. So we always ask, as one of, I think somebody else also questioned that one, and we always ask for drain test, and if the drain test give you, and generally drain test give sufficient bearing capacity, generally if we perform drain test, the soil bearing capacity improves a lot. Still then, if you need sufficient bearing capacity, then you have to retrofit the soil. But if after drain test you see that sufficient bearing capacity improvement is there, no need of any soil improvement or soil retrofitting. Samuel, which correlation should you use for determining share velocity? There is plenty of correlations. Recently, I have asked one of my students to find out correlation among SPTN and share velocity. In Bangladesh, we do not have have sufficient. One of my students has developed one, but it is not sufficient. So to develop a sufficient correlation, you need at least probably 400 SPT value data and 400 shadow velocity data. That is sufficient data, because otherwise the correlation is not good. And also you need to have correlation for sandy soil, you need to have correlation for clay soil. Then you can use those correlation for determining shadow velocity. But until and unless we have those, it is better to use correlation developed in other countries, like in Japan, USA, and China. They have sufficient correlations. And if you if you look for papers, you will find even in 2020 and 2021, at least I can provide you 20 examples, 20 references we have developed correlations. Because under COVID situations, there are lots of papers in this topic, on these topics. As I mentioned, if you do not have SPT, there is a lot of correlation you can generate, but it is preferred to go up to 30 meters. Share of velocity, there is correlation to go up to 30 meters, but SPT is the prerequisite. According to our new building code, you need to have knowledge up to a depth of 30 meters. That's 100 feet. It is not very expensive in our context. I think for all the projects up to 30 meter depth, we can easily assess SPT value up to a depth of 30. Then what value should we consider as share velocity of engineering bedrock for Dhaka? For engineering bedrock, I think you can, for residential building, you can assume 400 meters per second. For other important structures, as I mentioned, I think 760 meters per second or 800 meters per second as defined in our code. I think you have to go up to 200 meters as at least. But sometimes for some locations you have to go up to 300 meters. But if you want to study using engineering bedrock for other projects, not very important projects, you can assume engineering bedrock at where shear velocity is 400 meters second. And it is, you will find probably within a depth of 40 meters to 50 meters, you will find that. Okay. This question, Samuel again, shear modulus reaction curve. Generally, Professor Sid and Idris, back in 1970, they have developed shear, this kind of curve for sandy soil, clay soil. You can use those. Those can be found in the literature, and if you Google, you will find both the SHADE program and its manual over there. Those correlation or those reaction curves are already provided. Okay. Rul Kudus, I have already given this answer. For this particular site, you have to develop your own time history curve based on expression response curve and as well as the bedrock PGA value. Okay, and using imaging time, because directly you cannot, for any site directly you cannot use it. Even if we have data for, say, Jumna Bridge, we cannot use for Dhaka soil. It has to be matched for our own response curve for Dhaka. Directly you cannot use the time history. Okay, again, Asan. The site class match with soil classification, loose sand, medium sand, but 30 meter board depth is not possible. For low cost project like residential building, generally the site instrument found up to 15 meters. Yeah, it's true. How do we determine the class? That will be a challenge. But if we have very good correlation between SPT and shear velocity, we can use, because, but the thing is, you do not have SPT value beyond 15 meters. That will be a challenge, but I know there is a lot of correlation developed using 30 meter shear velocity, but if we do not have more than 20 meter, 15 meter, we can estimate shear velocity between 15 to 30. I think you can look into that those papers and develop SPT correlation where you can estimate SPT value between 15 meter and 30 meter. Use those ones. We need to do something about it, and I think in future in the building code we need to propose something. But currently we do not have any such thing. But I think there are some papers. You have to Google and search some papers where there are extrapolation of SPT value from beyond 15 meter or beyond 20 meter to get 30 meter. I think there are some papers. So you can search for those. But if you have really up to 15 meter data, you cannot assume values beyond 50 meter. You need to use some kind of correlation and make some sensitivity analysis, because SPT value suddenly changes in a certain depth. So you cannot just assume. You need to have to use some kind of correlation and several one to come to a conservative solution. Okay. What is the reason behind de-amplification of motion underlain by clay soil? It depends. It depends. Clay soil sometimes softens up. There is some hardening soil model, or some issues are there, but not always in clay soil it de-amplifies. So we cannot directly say that for clay soil it de-amplifies. Sometimes even for sandy soil it de-amplifies. It depends on the total layer, total soil column, and that's why not one earthquake time history data, you have to at least use 10 time history, generated time history. Only one time history will not give you the total picture, because the soil over there, soil condition for a particular site has the natural period, and the input time history has a different natural period. So you have to combine those to see the sensitivity. So you have to make some sensitivity analysis. So just seeing the one clay soil is showing de-amplification for one time history will not be enough. So you have to make some sensitivity analysis using several time history data, and then you have to reach a conclusion. Okay. From which reference we should consider 30 meter depth for the site classroom? Is it from EGL? Generally from EGL, but it is mentioned, but because it is for the site, it is not for the foundation alone. So I think it is the site classification, the 30 meter depth has to be considered from the top surface, EGL. Okay. Again, we lose soil at top layer, 20 meter affect the soil corrosion at top. That means the raft is, if the raft is positioned at 20 meter depth. Yeah, that is a good question, because initially where you said the bottom foundation for shallow foundation will not have much effect. But if the raft is put at 20 meter depth, 20 meter means 6 meter basement, I think then you have to make site response analysis, because as I mentioned, site classification is in for, because if you put foundation up to a 6 levels foundation, that minus 20 meter, it has to be a very important structure, large structure. So you have to perform site response analysis. For less important structure, 30 meter depth is enough. But for a project where you are putting 6 basement for up to 20 meter depth, you have to perform site response analysis. Yeah, you can use longitude, latitude to get the earthquake data from that source. Because generally, thumb rule is, in our region, 1 degree is 110 kilometers. So roughly you can assume 3 degree to get data for 300 kilometer radius. Okay. So it is already, Mr. Engineer Wahid asked, but the answer is there. There is only 4 zones over there in the PNBC. Shafi, can you provide us reference to calculate ground improvement method like sand pile? In fact, there is tons of papers on ground improvement technique, but one of the good book is Houseman's book. Houseman has a book on ground improvement. You can find in the new market. I bought it probably 20 years back. And recently he has published a newer version. So you ask for ground improvement or ground improvement. Book name is either ground improvement or soil improvement by Houseman. He's an Australian author. It is very comprehensive. Yeah, we can use, but what is the use? Generally, we have to have surface PGA. So why we need to have PGA value at different surface? I don't know. But all the methods mentioned, you need to have PGA value at the surface. Okay, Naim is asking, if you take the zone coefficient value from GPS coordinates, it varies from the table mentioned value. This happens especially for the boundary line. Yeah, on boundary line, it is a challenge. If we want to be conservative, it is better to have larger value. So if it is a boundary between the two zones, I will recommend you go for the larger value. Okay. When the end bearing capacity must be ignored of a pile foundation only consider scale when the end bearing capacity must be ignored pile foundation. It depends on the situation. Sometimes, say, if a pile is designed as a friction pile, you don't have end bearing, or if you think the foundation bottom pit is not cleared, that means there will not be enough tip resistance, then also you can neglect the end bearing. It depends on the situation. And if you are confident that your contractor has properly cleaned the pile bottom, then you can still consider bearing capacity, but factor safety may be used. Higher factor safety may be used. It is better to use higher factor safety for end bearing than friction. Okay. In Bangladesh, lots of projects, jet grouting I mentioned, for Akich factory in Bhaluka, then 2 or 3 projects in Chittagong EPZ, then nuclear Rupur power plant project, then there's the PGCB project, then there are several power plant projects. Currently, we are using in several projects in the coastal areas, as I showed some pictures. And jet grouting can go up to 35 meters. More can be done, but our equipments in Bangladesh, which we have, several equipments we have in several companies, I think they can go up to minus 35 meters. But all over the world, there are some machines which can go much deeper. For soil liquefaction, it is very simple test. Grain size analysis and plasticity index, or liquid limit plasticity limit is required for liquefaction. Time again for classifying the seismic class of soil, we need 30 meter information. Definitely, the soil 30 meter should be considered from surface level. No, it depends. As I said, generally for shallow foundation from ground level is okay. But if it is deep foundation, or if you put, say, as one of the engineers asking that up to 20 meters, then you have to make site response analysis. Not 30 meters is enough, because important structures you have to go much deeper. For multiple basement structures, it is important to perform site response. And if you follow the building code, the current building code, for C and D type, you have to perform site response analysis. For clay soil, it is not very, for clay soil, it does not improve much. Cement grout is more, it improves a lot for sandy soil. But clay soil, sometimes we have used, but does not improve that much. One meter plateau test, up to what depth does this reservoir represent? We have not done this kind of study, but since we have found that it is much reliable than what we use generally. Generally, we use in Bangladesh 1 feet dia or 2 feet dia. 1 meter dia is much bigger, so it is relatively reliable. But otherwise, there is no other method, because we have used CPT along with plate load test. So we have 2 methods we have used. So as I mentioned, just plate loaders is not enough. Okay. So reliability is a relative thing. So we have to use plate load along with CPT and SPT. For Rahman, plate load tests have limitation as the influence zone is very short. Yeah, definitely. Because because there is a criteria over there that surface soil has to show bearing capacity more than 80 kPa. That's why plate load test has been done. But basically, CPT and SPT probably is good enough. I have not done that as special moment frame governed by special design category D based on soil type. Can we modify it from special to intermediate moment frame? Probably it can be, because soil, if the soil is improved properly, the soil condition will be improved. And according to me, we can change the design category type. It is possible, I think. But you need to invest a lot. That you have to also remember, because soil improvement is expensive. If we need to improve the whole lot, you have to, how to say it, there will be lot of cost involved. Same question again. When to use sand compression pile as an effective method? Soil special for loaders. I think sand compression pile is you can use, because locally because Abdul Monin Limited has imported a very sophisticated equipment, but in reality, I have observed they have used locally improvised sand compression pile. I think for small buildings, 5 to 6 story structure, for clay type soil, we can use sand compression pile. But if the soil condition is not clay, I think it is better to use jet grouting. For clay, it is preferred to use sand compression pile. Sand pile is Kitazume. I think it is written by one of the engineer who questioned. Kitazume's books on sand compression pile. You can Google it. It is there in the internet. Permeation method and jet grouting has some differences. Basically same, but in the grouting technique, there is some difference. In case of soil improvement of cement mix with sand and deposit, will bearing caps improve? In case of soil improvement, if cement mix with sand, for shallow foundation and if the soil depth is not enough up to depth, that means if you do not need to improve more than say 3 meter or something, probably you can use cement with sand, or you can still, if this sand is loose, what you can do, you can improve the soil, you can excavate the area, you can put silt sand and make very good compaction. We have done it and we have got improved, good result. If the shallow foundation is there, and if the if the soil condition is poor after shallow depth.
Professor Ansari,
Yeah.
can you read the questions that you're answering? I guess some people are
Okay.
confused.
Okay.
They don't know which one you're answering. Sorry.
Okay. Okay, sorry. There is so many questions. Sometimes I'm asked question. Okay. Is there any minimum height of retaining wall or basement wall which we need to go for determining dynamic lateral pressure? It depends. Generally, retaining wall we prefer. Generally, we put probably for 2 basement, 3 basement, and even if 1 basement, we need to estimate that one. We have done it for several projects because it has a lot of effect. If water content is more, then chance of liquefaction is more, but why the liquid limit is less than 36% more than water content? Because it is showing this liquid limit is higher, means soil will be more saturated. That's why more chance of liquefaction. In the slide, LL shows less than 36%. Is it correct? Yeah, it is correct. Liquid limit is less than 36%. It is also there. 4. mentioned some soil improvement methods for clay soil. For clay soil, you can use PVD. You can use PVD. You can use sand compaction pile. And book is, I already mentioned, Houseman's book on soil improvement or ground improvement. Okay, then Indrajit Kumar Paul, how much SPT value that we understand no recording? It is not a fixed thing. Although some people say that if it is more than 30, no need of liquefaction. But if your PGA value is pretty high on the surface, you may have liquefaction if the SPT value is more than 30. That's why you have to make you have to get the PGA value at the surface. Then, so it is not a fixed value. I don't understand what do you mean by base separation in the context of earthquake. If we improve the soil beneath the foundation, I think, I don't know whether you are meaning that one. Probably there will be no base separation at all. But when the foundation condition is poor, then base separation generally happens. How much SPT value that we understand? I think I have answered that one. Please tell me the basic difference about mat and raft foundation. I don't know. For me, it is almost same. I don't know. I do not find any much difference between mat and raft. But probably officially there is some difference probably. But when we design, I think we design same. In some locations, the special moment frame is governed by seismic design. Can you modify? Yeah, I have already answered that question. That probably if we improve the soil, Hamdul Bari's question, we can change the design category, seismic design category. Can we use skin friction of pile for use of pile depth more than liquefied soil in soil liquid susceptible area for calculating pile capacity or on the pile area? No, as I mentioned, even you use pile, you need to improve the topsoil, because if the soil is liquefied, the pile will act as a, how to say it, as I mentioned, probably more, how to say it, ductile, slender. So it is, so whether you use skin friction pile or whether you use end bearing, it doesn't matter. You need to improve the soil. If the soil is susceptible to liquefaction. Is there any factor of safety in CPT test? Yeah, CPT test, similar to the SPT test for liquefaction susceptibility, CPT has also factors. Same way. Site specific response rate. When we should use site specific, what is the difference between site specific versus code based? Generally, code based is average value. In the code, for several locations, we have assumed we have developed the time history and we generated time history and we developed the response curve and then we averaged. For a specific site, we will perform site response analysis for the specific site and we will develop time history and we will generate response pattern from that site. So the difference is code and average value is there. But for specific sites response, we will generate for that particular site. It will be based for that soil condition. Okay, that is the difference. Code is some kind of average value. Considering the water table in Bangladesh is generally shallow and including the effects of regular high rainfall intensity in rainy season, 80% as well, shall be drain test applicable out there? Drain test is a different issue. Drain test is the condition of the soil. It does not have to be the local soil condition or local water table. So drain test is a condition where you get more conservative or more reliable value, because the soil building is standing there for 10 years or 15 years. So the condition is similar to the drain condition. That's why you can use the drain condition. Okay. There is a question of overturning moment is okay. Okay, just if overturning moment is okay for a building, then there is no rotation of foundation. If rotation occurred at base, then in case of isolated footing, would you use fixed support? But there is a different issue. It is a modeling issue. One is the modeling issue, one is a real field issue. overturning moment is okay for building, then there is no rotation of foundation. But I think for isolated footing, we generally do not use fixity. Generally for deep foundation or pile foundation we use. What is the basic condition for design for rafter? Basic condition, it is a very elaborate question you asked. I don't know what is the basic consideration for design of mat. It depends. If the soil is poor and if the whole area is, if we put foundation in the whole area and there is a little gap, generally we prefer mat foundation. But nowadays, not only mat, we nowadays prefer mat pile raft system, where some load is taken care by pile and some load is taken care by mat. So it is much better than mat or better than pile alone. Shear band is the question by Mohammad Ilyas is shear band is a very research oriented topic. I think real field there is no much, the impact is not much. Although you have asked question, this is much more theoretical. Practical implication is not that much. For low-rise building which has isolated footing belong the footing of some engineer size 1 to 2 feet compacted sand with big beds. Process for shallow foundation probably you can use if the soil beneath is not very much susceptible to liquefaction. If it is up to 3 feet, 3 meter or 4 meter, probably you can improve some other technique. But you have to be very careful. If the water, you have to consider the water table also. Subgrade modulus, I think generally we use, what is the suitable way? Using the plate load test. We generally use plate load to estimate the subgrade modulus. Such some consideration that need to be taken care of to need to consider different stages of foundation design in hilly areas. It is a tricky question for hilly areas. It is very difficult. You have to first consider the soil slope stability analysis. If this soil is slope is stable, then you have to anchor it, because in this slope you cannot put foundation that easily. Sometimes even it is in this slope, you have to also put very good anchor. Sometimes you have to improve the soil using some kind of geotextile or geogrid or some kind of protective measures you have to use. Otherwise, in the slope, you cannot directly put the foundation. Some kind of geotextile, geogrid, or some kind of anchoring technique you have to use in the slope. What do you think about the performance of sheet pile confinement around the project area in comparison with other available? I don't know, Partho, what you mean by just sheet pile. Sheet pile is generally used for some structures which are very close to the water body or some kind of water body, or sometimes in also some hillside also you have used sheet pile. About the purpose of sheet pile confinement around the project in comparison with other, but sheet pile is very expensive. Because generally sheet piles we use for temporary purpose. We use this sheet pile, then we use the foundation, and then we try to take out the sheet pile so that we can reuse it. So if we keep the sheet pile, the cost will be pretty high. So it is better to go for remedial measures, soil improvement technique. By long period and short period, it is depending on the soil, because response spectra, you see response spectra is developed from 0.1 second to 10 seconds. Generally, according to ASC, I think it is defined probably 0.3 second is the short period and 1 second, sometimes 2 seconds is also defined as the long period. It is defined also in ASC. I think in our code it is 0.3 second and probably 2 seconds or 1 second, I forgot. But 0.3 second is the short period and long period is either 1 second or 2 seconds. Could you please give some idea regarding the applicability samples? For example, already I have given the answers, same questions. Just people with the bearing capacity. Bearing capacity evaluation, you have to either depend on SPT value for sand and for unconfined value or triaxial value or drain value, direct shear value. For clay, you have to perform either triaxial or unconfined. And for sand, SPT is enough, but sometimes if you are not satisfied, then you can perform some direct shear test. Yeah, nowadays, as Naim has uttered, nowadays we need also geotechnical earthquake engineer. Usually we used to have lots of structural engineers, but you can understand from today's presentation that we need to have knowledge on geotechnical as well as geotechnical earthquake engineering. And this is a field where I think many of our students and like you have to move, because there is a lot of opportunity, because we are constructing in a very soft soil, sometimes very loose sand. We need to know a lot of issues like soil improvement technique and other techniques. So we have to have some more knowledge, and there is lots of books. You can go through the initial book. You can go for geotechnical earthquake engineering is the Kramer's book. It gives you an initial knowledge about geotechnical earthquake engineering. So I think these are the main questions. Okay.
Thank you so very much, Professor Ansari.
I tried to answer all
No,
the
this is very kind of you and very patient of you to answer so many questions after a long lecture, but very nice thing to
I
do.
tried to, because yesterday Jonas sir could not. That's why I thought I will cut short and try to answer most of it.
No, that's wonderful. I think we have had two very successful geotechnical seminars. I would like to address two things. One came up even yesterday with isolated footings, whether you can have fixity. I think
probably you will answer better, because I'm not very much accustomed to that.
You said the right thing. I have never seen anybody take fixity with an isolated footing. An isolated footing has to be pretty massive to provide fixity. So that is not a good idea. The other thing that came up twice today, change the seismic design category by soil improvement.
Yeah.
I do not think that's a good way to think, because the seismic design category can change only if the soil type at the site will change because of soil improvement. And that, as Dr. Ansari said, is very difficult to accomplish. It will be very expensive. That's not a good way to think. We
have only done it for Rupur power plant, Dr. Ghosh. Only Rupur power plant, we have expended almost $500 million to improve that one.
Yeah, this is what I'm saying. Yeah, as I said, I'm not saying it cannot be done, but it's not a good way to think. That's not how you should approach a problem typically. So, okay, with that, I thank you very much, Professor Ansari, one more time.
Thank you. Welcome.
I think these two seminars have been wonderful, and you are right. I think geotechnical aspects have to be emphasized because of all the development that is going on in the country. Thank you.
Okay, thank you.